All right, this is the second hour of Physics 1C for April 22nd. We're going to be talking about the forces of magnetism on wires that have current in them. Okay, so here we go. We have a picture here. This is from your textbook. In this picture, we have these little X's, which remember, these are vectors that are pointing into the page. There's a vector field that is the magnetic field that's going into the page on this particle, or on this, this little cylinder right here. This cylinder is a wire that we've cut off in pieces that has a current flowing through it. There's a symbol J here, which represents current density, but nonetheless, there is a current that's flowing through this wire up in this direction. There's an electric current. And remember that electric current is simply the flow of electrical charges from within the wire. So, because there are charged particles that are moving through this wire, and because we know that a particle that is placed inside of a magnetic field that has both a charge and a velocity will feel a force, then as indicated on the diagram right here, if the force is up and you use your right-hand rule and go from velocity to magnetic fields like this, then your thumb points to the left. So there's going to be a magnetic force that goes this way. Now, this force is going to be placed on every single charge carrier inside of here. And within a certain volume, there could be something like 10 to the 30 charge carriers, 10 to the 30 electrons. And the effect of that is that if you have all of those different charged particles that are feeling a force, then the net effect is that the wire itself is going to feel a force. And we'd like to know how big that force is, right? So the question now is basically, what is the magnetic force on the wire, due to the fact that its components are moving? All right. So what we're going to do is we're going to look at kind of a cross-section of this wire right here, like this. Cut off a cross-section of this wire. Well, I guess we can just use the whole thing, right? Based on the numbers that are here. Because then we know that this is L, cross-sectional area A. So within this volume right here, we could say that each particle is going to feel a force that's going to be the charge of the particle multiplied by its speed, which we call that speed that the particles are moving the drift velocity. And the drift velocity then just gets multiplied by the magnetic field. So we say basically each particle feels a force that would be equal to this. So this would be the force on one particle, called the force on one, QVD. In order to figure out the force on the whole wire, though, we would need to include all of the particles that are in here. And to do that, we can say, if we know that the number of particles per unit volume, so this is the number of charge carriers divided by the volume. And then the volume is just going to be the area of the end cap multiplied by L. That's the volume, right? So if I take the number of charge carriers and I multiply by the volume, I can get the total number of charges we have, which will be giving us the total force. So if we just take this, which is going to give us the total number of particles, N times A times L, and we multiply by the charge on a single carrier, Q, and then times the drift velocity times the magnetic field. And I'm going to go ahead and turn this into a vector equation now, because we know that if we take the velocity vector and we cross-product it with the magnetic field, then that's going to give us the direction of the force. Maybe we wait one... Let's wait one step before we do that. Well, that's okay. I think this is okay. So now what happens is we look at this and we say, in order to keep it as a vector, I'm going to say that we defined current density to be equal to, I believe it was, so it's charge divided by area, right? So I think it's N times L times Q times VD. I think that's what the current density was. And just to, I pulled this up in the textbook so I could point to it, because this has been quite a while now. But long, long ago, when we first introduced current, this was our model. We said there's charge carriers, and they're each moving with this constant velocity that we call the drift velocity. And we said that given that, we can define this thing called the current density right here. Oh, there's not an L in it. That's the thing that's wrong. Sorry, it's just N times Q times VD. That's it. So the current density is given by this right here. N times Q times VD. Right there. So since those show up here, you have N, Q, and VD, then what we end up getting is the current density. Here. We have length times the current density, NQVD. So there's still an A, right? And that's cross product with the magnetic field. And then what we're going to do is say, well, if we take J and we multiply by the area, J is current per area, so this is going to give us the current if we just take the absolute value of this. So we end up getting J times A is current, so we now have I, L, and B. And we got to do something kind of funny here. This is why I was reluctant to put this cross sign here, where we say, well, current density is a vector that points in the direction of the velocity. Current is not a vector. So if I still want to have a cross product right here, I'm going to have to turn the length into a vector, because we know length can be a vector, right? So what I'm going to do is I'm going to say define a vector that points along the length of the wire like this, and call that vector. I'm just going to write it over here because it's hard to see. I'm going to call that vector L. Okay? L is going to be a vector that points in the direction of the current, and it has the magnitude of the length of the wire, basically, right? So I'm going to shift my this is a little bit of weird vector manipulation here. I don't know how else to do it, though. I'm going to shift the vector over to that length L right there. And then we get our answer. This is our answer. The force that's placed on a wire that has current in it is going to be equal to IL cross B. So it depends on the current, of course, because the current controls how fast the particles are moving. Current is directly proportional to drift velocity. So you increase the current, the force is going to get bigger. It also includes the length of the wire, and it includes the magnetic field. So the bigger the magnetic field is, the bigger the force is going to be. The bigger the length is, the bigger the force is going to be. Okay. So this is our force that's placed on a current-carrying wire due to a magnetic field. Now, this is going to work really well for a straight wire, but if I have a wire that's curved like this, let's say, for example, and that wire is placed into a similar type of magnetic field, then we have to do something a little bit different. So if I have a magnetic field here, and I have a wire here that carries some current I, then there is going to be a force on this current-carrying wire, except what I'm going to have to do is I'm going to have to break the wire up into little pieces that I'll call DL, like this. And then what we'll do is we'll say that if the wire is not straight, we'll have to define kind of a small force element on every piece of it, and that is going to be written like this. The current is going to be the same throughout it, because that's the way the current works, but we'll do a DL cross B. And we'll see that we'll use both of these equations right here. Now, I'm going to show you a video of how this works, but before we look at the video, I'm just going to ask, does anyone have any questions so far? So let's just kind of verify to see if people understand. Suppose I have a wire, and it carries a current in this direction, I. Which means that the, quote, L vector also points in that same direction. We kind of draw it on here. L would be this way. Can you all tell me by like answering in the chat, what would the direction of the force on this wire be? Can use your, okay, B is the dots here, by the way.
Or just...
Go ahead and answer in the chat what direction you think it is. Down, right? It is perpendicular to L, John, but which way? Because like it can be perpendicular this way, right? Or it can be perpendicular this way, right? Is X into the page? In my picture here, dot. Yeah, let's have a little reminder of what these mean, because I know it can. This means out, and this means in. My way of remembering this is just think of an arrow, like a bow and arrow kind of arrow that has feathers, right? And when the arrow is coming towards you, it's the dot, because you would see the point of the arrow, right? So if your eyeball's over here, you'd look at this and you'd see the arrow coming towards your eye, and you'd say, okay, it's like a dot. But if you're looking at it on this side, you're going to see the feathers, right? And so these are the feathers and these are the dots. Okay, southeast, that's correct. So the direction of the force on this wire is going to go this way. And again, just to kind of reiterate why that's the case, now this is interesting because it's not a force that is exerted in one location, right? It's actually kind of like over the whole wire. The whole wire is going to feel this force, basically, which is really quite interesting. Yeah, so the reason it goes that way, you basically, for this one, you just point your fingers in the direction of the current, and the current's going up that way. And now I need to rotate my palm so it's facing the direction of the magnetic field, and your hands curl, and your thumb points down this way. I don't know if you can all see that, but it was V this way. Magnetic field's coming out, so southeast. Exactly. All right. What's another one we can do? What if we have a magnetic field that goes this way? So there's B, our vector field. And now let's take a wire and let's have it run this way. So there's I. Again, what's the direction of the force now?
Into page.
Okay, into the page. Let's see. Yeah, so I is up. B is right. Thumb is in. Every time I do this, my hand hurts. But yeah, so now our force would be into the page. That would be FB. That would be FB. Again, it's kind of all along the wire. Okay, now that we can kind of predict the direction the force might be, as long as we know the direction of the current, which is easy to know, and we know the direction of the magnetic field. That's right, Kyle. L is in the direction of the current, exactly. This L basically just points in the direction of the current. I always think about it as being like L times I cross B. I just think it's current cross B. Personally, that's what the way in my mind, the way I think about it. But really, it's L cross B. This is the proper way to do it. All right, let's watch a video where we can see this, because I can't, unfortunately, show this to you. But we could have done this in the lab. I could have shown this to you, but we unfortunately can't. So we're going to watch this video. I need to switch the screen. And this person is going to demonstrate this force. It is a really kind of, just like anything with magnetism, it is a very strange and surprising type of force, I think. Okay, I'm going to start playing. If you can't see if you can't hear the audio, just type something in the chat. Okay. Here we go.
So I have here a large magnet, south pole, north pole. So the field is pointing up. And then I have a big...
Can you all hear it?
Yeah, I can.
Yep, I got it ready. Isn't that cool? It's like almost like magic.
It is. Oh my, like, if you're definitely like medieval.
Yeah, yeah. You show this to some peasants from the 800s.
You'd be God.
Yeah, you're like a sorcerer.
Not a stake.
You're basically a sorcerer at that point, right? You get burned at the stake, probably so. Start weighing you against a duck and throwing you in ponds and seeing if you float. Okay, so you could find all kinds of videos of this kind of stuff if you find this interesting, but it's just, you know, it's showing that, yeah, it's and I love how, like, all you have to do is just switch the direction of the node, the terminal, so you reverse the direction of the current and it instantly goes back the other way. Not only that, but it's basically an equilibrium now, right? It finds an equilibrium between the two forces that are acting on it, which are basically gravity, which is down, and the magnetic force, which goes this way, and the tension, which is kind of at an angle up like this, right? So it finds a balance, and then it kind of just stays there. Yeah. So again, this magnet. I just go ahead and pause it real quick here to look at this magnet. We have a magnet almost exactly like this in the laboratory. So I had been saying in the you know, when we'd been talking about this. Here, let me switch the screen back to OBS. So this type of a magnet is basically how you can produce a very nearly uniform field, because the magnet is... What's up?
You're still seeing the YouTube screen.
Yeah, I know.
Oh, okay.
That was intentional. Can you see my mouse that moves over the YouTube screen?
Yeah.
Okay. So I just wanted to talk about the way that this kind of magnet works. So basically the magnet has a north end and a south end. I can't remember which one he said was which, but one end is north and one end is south. Let's say the bottom one's north. So if that's the case, then what happens is that between the poles, you get a really strong uniform magnetic field right here between the poles. It's almost exactly like a capacitor with electricity, where you get a uniform electric field. But by putting the north and the south pole of the magnet very close together like this, you get a nice uniform field between the poles. And yeah, it's nice to be able to produce things that are simple. A uniform magnetic field's, you know, quite simple. So, yeah. Okay. Let's do a calculation, a couple calculations. So here is the first one we want to do. Shift all this junk over to the right so you can't see it. So this is a pretty simple problem. We have a conductor. It says a straight horizontal copper rod carries a current of 50 amps, which is just a massive amount of current, from west to east in a region between the poles of a large electromagnet. In this region, there is a horizontal magnetic field towards the northeast that is 45 degrees north of east. So B are these vector lines that are drawn right here. And that's north, that's east. With a magnitude of 1.2 Tesla. We want to find the magnitude and direction of the force on a 1 meter section of the rod. And then it says, while keeping the rod horizontal, how should it be oriented to maximize the magnitude of the magnetic force? And what is the magnitude of the force in this case? Okay. So our equation for this type of situation is what we just derived. The magnetic force is equal to the size of the current multiplied by the length of the wire, cross product with the magnetic field. And I believe we have all these pieces of information here. In order to find the magnitude, what we need to do is we just need to write down the current times the length times the magnetic field, and then we need to put inside of here the sine of the angle between the L of the wire and the magnetic field, which they've been nice enough to draw for us on this diagram. L points in the same direction as the current, so it goes to the right. The magnetic field goes kind of at an angle of 45 degrees relative to that, so there's an angle between the two of them that's 45. So for us here, this is going to be the sine of 45 degrees. And we can then plug all the numbers in. Can you all tell me in the chat the direction as I'm writing this down? What will the direction be? So I is 50.
could be out of the page.
Out of the page? Yeah, I agree. 50 amps. The length of the wire was 1 meter. The magnetic field is 1.2 teslas. And the angle. So we will get 42.4, thanks. Newtons, and if we want to make that into a magnetic or to a vector, we would say out of the page. Or in this case, kind of like probably up, right? If north is this way, east is this way, west is this way, then I would suspect out of the page means upwards, right? So there we go. Anyone have any questions? Pretty easy. Okay. Next it says, so this is part A. So next it says to find, while keeping the rod horizontal, so we leave the rod the same, how should it be oriented to maximize the magnitude of the magnetic force, of the force? So that means basically keeping it in the same plane, horizontal as in parallel to the ground, basically, right? Or parallel to the horizon. How should we orient this wire to get the maximum magnitude of the force? What do you all?
Perpendicular to the magnetic field.
Yeah, exactly. It's basically, we want the wire to basically go this way now, right? If the current goes that way, and the magnetic field goes this way, then the angle between the two of them is going to be 90 degrees. And then when we do our force, it'll be FB is equal to ILB times the sine of 90 degrees, which this is 1, which is the biggest that the sine can be. So our size of our force now is just going to be 50 times 1 times 1.2 times sine 90, which is 1. And I believe this is going to give us like 60 amps probably, or 60 newtons, sorry. Is that right?
Yep.
Okay. And if it was, or it would still be out of the page, right? Yeah. Okay. Pretty easy, right? Okay. Let's look at one that's a little trickier. No. Why am I doing that? I just want to stay on one note. Let's look at a curved wire. Okay, so magnetic force in a curved conductor. So now we have a wire like this, where the current is flowing around this circle here, semicircle, and then off to the left here. And it says, in the figure, the magnetic field B is uniform and perpendicular, represented by all of these dots right here. And, to the plane of the figure, pointing out of the page. The conductor carrying a current I to the left has 3 segments. One, a straight segment with length L perpendicular to the page. I don't think we can see that one, right? That's, the current is coming kind of out from here. There's a wire that goes into the page, this direction, and it goes in right where that X is right there. That's the first segment. And then it says 2 with a semicircle of radius R. So that's this one here. And then another straight segment with a length L that's parallel to the x-axis. That one's here. So we want to find the total force on each of these segments, okay? So let's start with the first segment. Now again, the first segment is the one that comes basically out into the thing. You can't see it, but it's kind of coming out from here. What's the force on that one going to be? So it should be I times whatever the length is, times the magnetic field, times the sine of what angle?
It's 0.
0, I would put 180,
Yeah.
but it doesn't matter, right? 0 is also right. L is this way. No, sorry, L is in. Magnetic field's out. So that's where I get the 180. But 0 is fine too. They're anti-parallel, So this is going to give us 0 because this term is 0. If the current is flowing parallel to the magnetic field, there's no force, or anti-parallel, as it is in this case. Okay. Second segment. This is the hard part. We could do the third one first. Third one's easy, right? Second segment was hard. So for this, what we're going to need to use is the other definition that I made for the magnetic force, which is that if I have some kind of a curved object, then I need to break it up into little tiny parts and say that the size of the force on each little part that has a line element dl crossed with b. That's how we're going to do it. Okay. Now, they've already drawn a lot of this stuff for us here, but the idea would be that within a particular segment of this, what we could do is we could break up. Let me use the same color they use. They use like this dark bluish color. So within this segment, we could break up the entire wire into a bunch of little DLs like this. Okay. You break it. You basically turn it into a bunch of little tiny short segments that have length DL. Don't worry about the D. The DL just means it's a tiny piece, right? I know that we're obviously going to use calculus here, but don't worry about the fact that we're going to use calculus. Don't let your brain start just immediately thinking about calculus. Just understand that really what this means is DL could literally be like a millimeter. It could be a tiny little distance. We could just break this up into 1 millimeter long segments. We could find the force on every millimeter segment and then add them all up, and that would give us an answer. That's basically what we're going to do. And we're going to use calculus, we're going to use integrals, but that's ultimately what the integral is doing for us, is it's composing a Riemann sum with, you know, infinite precision. All right. So we need to know something about this DL. Now, when we look at, for example, this piece right here that they've constructed right here, and they've already shown you what the answer is, right? But what would DL cross B look like in this case? Because DL cross B gives us the direction of the force, right? So if DL is this way and B is coming out, then you get a force that points up and to the right. Do you all agree?
Yes.
Okay. But when we're over here, can you tell me what would the direction of the force be at this location? Over here about 90 degrees or so away. DL's this way. What direction is the force on that piece going to be?
Northwest.
Northwest, exactly. Exactly northwest. So with this piece, the force is this way. All right. So we're going to need to kind of add all of these up as we go through here, right? And I believe what we could probably do is say that when we get over to this point here, right, it's also going to have components. It's going to have a dfx that goes that way, and it's going to have a dfy that goes up, right? I'll just write, this is going to be dfy, just like it's been done over here. And the bottom one is going to be dfx. Now, if I pick exactly the same angle over here, but just relative to the negative x-axis, what do you think we can do with these x components?
They'll just cancel out.
They should just cancel out, right? So if I pick a piece right here, I can find another piece over here where the x components are going to be equal to each other. The y components will be equal to it too. And they should totally just cancel out. That means that really we only need to find the y components, which is great because I don't even want to think about what would happen if we needed to do an integral where you have to do a cross product the entire way. That sounds like a nightmare. But if we can just say that all I need to do is just look at the y components, that should be easy, right? Because then we can just say, well, it's going to be equal to I dl cross b, and then now I just need to multiply by the thing that's going to give me the y component, which will be what? What do I need to multiply by?
The sine theta.
Yeah. So if I put sine of theta on here, now keep in mind, normally we use the sine when we do the cross product. This is different. This is just giving us that y component, because dfy is going to be, I'll put it over to the left here, dfy is going to be equal to dfb times the sine of theta. All right. now we can say we also need to include in this the angle between L and B, right? So what is that angle going to be? Magnetic field is coming out of the page. DL is in the plane of the page. So what's the angle between L and B?
90.
90, right? So when we do this piece, that is just going to become LB sine of 90, which is just going to make it L times B, and that's great. So now we have I dl B, and then sine of theta is still sticking over from the fact that we just were finding dfy. Okay, great. So now that we've gotten rid of the vectors and stuff, we should be able to do an integral. As long as we get everything into the right kind of setup. And the way we'll do that is through a process. I'll let you all tell me. What do I need to do with this integral? Currents and magnetic field are going to be a constant, right? What about the sine of theta? Is the sine of theta going to be a constant? For example, if we compare the line element that we have drawn here, which has an angle theta with the horizontal with the x-axis, and I compare that to a dl, for example, down here, what's going to happen here? Are they going to have the same angle?
No.
No. So that means theta is a variable now, right? And it's going to change for every single dl. So how do I then make sure that dl and theta have the same variable?
Get DL in terms of theta.
Get dl in terms of theta. And how can I do that? What is dl going to be equal to?
It's
Arc
R
length.
d theta.
This is already theta. Use the arc length relationship, exactly. If it was an arc length s, that would be equal to r times theta. But if it's an arc length dl, then that's just r times d theta, where d theta is basically just the small angle that is subtended by this dl right here. Okay, great. So at this point, you all are kind of experts in doing things like this, right? Because this has obviously come up several times in this class, and this is not the last time that it's going to come up, where if I have a curved object, I'm just going to replace my line element, dl, with r d theta. It's just going to keep happening over and over again. So if we do that, then we end up getting r times sine theta d theta. And now we can do this. We want to integrate between what limits? Well, we want to cover this whole thing right here, with theta being measured from the x-axis right here. So what are my limits?
Pi.
0 to pi, okay. I agree. Or we could probably go from 0 to pi over 2 and double it if we wanted to as well, right? But doesn't really matter. Get the same answer regardless. So we have I times B times R. And my guess is we're going to get 2. That's just what I think we're going to get. Let's find out, though. So we end up integrating sine, which is going to give us negative cosine, I believe. And we need to evaluate that between 0 and pi. So let's just write that over here. That's going to be I, B, R multiplied by the... let's pull the negative sign on the outside. Cosine of pi minus cosine of 0. I'm pretty sure that's going to be something like -1 minus 1. And so we're going to get 2. Let's go back. What were we finding? We're finding the force on this piece, so let's call it F2 or something like that. Let's call it F2. What's the direction?
It should be upwards in the y direction.
Let's drop a j hat on there. And why was it up? Well, it's because we were only looking at dfy's because all the dfx's cancel. Now, if you'd like to, you could go through and you could use calculus to prove that the dfx's cancel by writing dfx is equal to I dlb cosine theta, and then also integrating. And what you're going to find out is that when you end up with a cosine theta here, and you integrate it, you're going to get a sine, and you end up doing sine of pi minus the sine of 0, which is 0 minus 0, so you get 0. So it will work out as long as you remember that because this is a vector equation right here, or this is a vector equation, sorry, that you do need to you don't want to do the vector equation without breaking it up into components first. That's what I'm mostly trying to say. All right. Anyone have any questions? Last piece is segment 3, so this is segment 3 over here, and for this one we have a length L, we have a current I cross B is up, and they're at right angles to each other, so this one is super simple. Just like the last problem, the answer for this part, only get one, let's call it F3, is going to be equal to just I times L times B. So our goal, oh, and this one's also up, so we could put a vector here, put a little j hat on here. So then if we sum up all of our forces, which is going to be F2 plus F3 because F1 was 0. I'll put F1 in here as well, but just indicate that this we found was 0. Then we end up getting, it looks like ILB, let's do it in order. So 2IBR, 2IBR plus ILB. And all of that is multiplied by j hat. Of course, we can kind of simplify this a little bit by factoring out the IB, and we'll get IB times 2R plus L times j hat. Does it want us to find the net force? Yeah, find the total magnetic force. So there we go. That's the answer. So this curvy plus straight segment would feel a force straight up. Does anyone have any questions? Okay. So the next thing we want to do is to take this idea of magnetic force acting on a wire, and we want to see what will happen if we use a loop of wire, a closed loop. See what effect that's going to have. We're going to call this the magnetic, it's going to be torque at the end of the day, but I'll say force for now on a loop. And a loop literally just means any closed loop of wire, so it could be shaped as a circle, a rectangle, a pentagon, whatever you want. Just, it needs to be closed in some way. All right. So I pulled this picture from another book because the picture in your textbook is wildly confusing. It's drawn in 3 dimensions on a flat surface, so it's very hard to understand what's going on. But I think this is a little bit more clear what's going on here. So we take a loop of wire right here that's been kind of broken into 4 segments, 1, 2, 3, 4 straight segments. Our loop has an area, sorry, not an area, a width of B and a length of A. And the entire system is placed into a magnetic field. Now the magnetic field only shows up here, but the idea is that it covers this whole region, okay? So the entire wire is basically just embedded in a uniform magnetic field. Okay, so even though the magnetic field's only drawn over here on the left, imagine that it just continues through, okay? So the whole thing is embedded into a magnetic field. And what we'd like to do is to figure out the forces, or the total force, acting on this entire object here. Okay, so let's look at them piece by piece in order, 1, 2, and 3. Okay, F1, and I'm going to put our equation we're using to solve this up here. Okay, this is the equation we're applying, IL cross B. So F1, can you all tell me what that's going to be? We need to do I times the length. What's the length? B times the magnetic field, capital B, multiplied by the sine of the angle between those two. What would that be? What's the angle between the current and the magnetic field?
180.
180.
180, okay. And so this is equal to?
0.
Yeah. All right, let's do F2. So F2 is going to be currents going down this way, so same current, I. This is one of the things that's really cool about current, is it doesn't matter how I shape my wire, the current is the same everywhere. Everywhere, it's exactly the same. And that's really nice for doing these kind of calculations. You don't need to figure out, oh, does the current get faster in this portion? Does it slow down over here? It's just the same everywhere. It's a nice uniform number. Okay, we need to multiply by the length. Okay, what's my length here? Well, it's this length here, which is A, and then times the magnetic field, and now times the sine of the angle between them. And with this one, we can actually throw a direction on here. The sine of the angle between I and B, what's the angle now?
90.
Okay, so this is 90 degrees. And what's the direction for this one going to be? So let's define a coordinate system. Let's call this direction the x direction. Let's call the up direction the y direction. And then let's call the direction that's coming out of the board at you to be z. So what would the direction of F2 be?
Positive z.
Okay, so we'll just call that k hat, right? Yeah, so you do I, which is down. Curl your fingers, and your thumb should be pointing straight at your face for the force. Okay, that's F2. F3 is going to be same as F1, I times B, and then what's the angle between the current and the magnetic field for part 3?
0.
Still 0.
Yeah, so this one's 0. So the top and the bottom ones experience no force, and then F4 is going to be current I, same, length A, magnetic field B, and again the angle between I and B is 90 again, right? But what's the direction of this one? So I, B, thumb in. So what would that be in coordinate systems?
Negative k?
Yeah, negative k hat. So there we go. We know that basically only the side 2 and side 4 feel any force at all. The other two, they don't feel any force. Okay? All right. So suppose what we did then with our loop is that we took a drill and we drilled a hole in the top right here, and we drilled a hole in the bottom here, but we still leave gaps so that the current can flow around the holes. Okay, and then we take an axis and we run it directly through our system here. Okay, so we mount the entire loop on an axis and we allow it to basically rotate. Okay, we allow it to rotate, and then what we do is we change our viewpoint. So we're going to look at this basically from the bottom. Okay, so the wire that's called 3 right here will be the wire that's in front. All right, and we're going to look at it. We're basically going to take the entire system, which is flat, and we're going to flip it so we look at it on its edge. Okay, and we're going to make it so that it is allowed to basically rotate around an axis O that runs through it. Okay, what that's going to look like then is my axis O is going to be right here. This bottom piece right here, this is side 3 that we're looking at. Okay, just to remind you, this is side 3. We're looking at the bottom edge. And now, when we've done that, the current flows in from the left side. That's why there's a dot, right? The current's coming out this way now. It flows across the front, so it's not drawn here, but I'll draw it in. This is the direction of my current now. And then it goes back in the other side. Okay? So we can then see that our forces, which were before F2 we had said was positive k hat, well, what direction is the z direction now? This is now the positive z direction. And this is now the negative z direction. Right? Because we've taken our entire system, we've flipped it, which means we've flipped our coordinate system too. So I think, tell me if this is wrong, but I think this is still the x direction, right? Is that correct?
Yeah.
Yeah.
And then now y is going to be the one. I think, what direction is positive y?
Pointing into the screen.
Into the screen, right? You want me to draw on here? I don't know. I don't know if it helps. Maybe use a different color. It might be a little more clear what's going on. So now, that's negative y. And positive y goes back that way. We flipped our whole coordinate system around, right? Okay. But this allows us to see what's going on really well now. Because we've allowed it to rotate about this fixed axis O, okay, what happens is that one side is being pulled up on while the other side is being pulled down on. So as a result, it's going to create a torque that tends to rotate the loop clockwise, right? Can everyone see that? If this side has a force up and this side has a force down and the front and the back have no forces, then it's going to rotate in a circle like this, right? And we can say that there's going to be a torque that's created on side 2, plus, if I add to that the torque that's created on side 4, then that should give me the total torque that's acting on my system. And remember how torque is defined? Torque is defined as the distance from the axis we call r, and it's a vector, and we cross product that with the force F, which in our case is going to be the force F sub B, right? Now to remind you how those vectors are drawn, in case you don't remember, R is a vector that's drawn like this, okay? And then we use R cross F. Now, we've been using these cross products all day, so hopefully you're comfortable with this cross product by now. And we can say now that our torque that we're going to get, what we're going to do is we're going to say clockwise torque is positive. So we'll define clockwise to be positive. Then both of these torques are going to be clockwise. So the torque for 2, let's just write it down beneath here. This is because we're adding clockwise torques. Let's just say torque 1 or torque 2 plus torque 4 is equal to the net torque. And torque 2 is going to be equal to R. How big is my R vector here now?
B over 2.
Mm-hmm. So we're going to just basically say B over 2 multiplied by force 2, and then it's a cross product, so we have to do multiplied by the sine of 90, because that's the angle is 90, but that's 1, right? Plus torque 4, the distance is also B over 2. Multiply that times F4. And that's going to give us the net torque. Let's continue over here. No, I don't want to do that. We'll keep going straight down. So B over 2 times F2. And then we can plug in what F2 was. So we'll have B over 2. F2 is equal to IAB. And then torque 4, or force 4 was here, multiplied by I times A times big B. You notice that both of them are exactly the same. That's our net torque. Now we can write on the right-hand side that our final result is that the torque is equal to I times A times B, because you do B over 2 plus B over 2, you just get B, right? Multiplied by the magnetic field. And what is A times B?
That's the area.
Exactly. A times B is the area, which I'm just going to call A, capital A. So this whole thing, which is equal to the sum of the torques, is equal to the current times the area times the magnetic field. That is a very simple result, right? Current, easy to measure. Area, really easy to measure. Just how long is this multiplying by each other, right? And the magnetic field, once again, is also something that you can produce and you can figure out what it is. And that will tell you exactly how much torque you have on this object. And what's going to happen is that the loop itself is going to rotate. And if you think about that, that's kind of powerful, right? If there was no current flowing here, there would be no force. But the moment that you flip on the current, that little loop basically starts to rotate, right? Now, how far is it going to rotate? Is it going to just rotate in circles over and over and over again? I don't know. I guess we'll have to think about that. But this is the starting point, and what we'll do is we'll look at what happens when there's an angle